in different kinds of atoms. Okay, so tonight's homework will have you figuring out how many protons, neutrons, and electrons are in that kind of atom. Okay. Okay, so to count the pieces, pieces we're going to count are protons, neutrons, electrons. How many pieces do you need to assemble an atom? Okay, next one. Okay. Keep them around just in case somebody forgets there someday. Okay. So, when we're talking about counting the pieces, there's some numbers that play an integral role. Chemists keep track of a couple numbers about atoms. The first one is the atomic number. And the atomic number is the number of protons. That's what it is. How many protons there are. If an atom has 7 protons, its atomic number is 7. If it has 8 protons, its atomic number is 8. So, but I like scientists when they're lazy. Why did they call this the proton number? Why did they call it the atomic number? Well, good. What do you think it was?
Because there's atom in there.
There's atom in there?
Yeah.
Okay. Well, actually, what it comes from, they came up with the atomic number before they knew there were protons. The atomic number was the charge you got when you knocked all the electrons off. And they found that those jumped by whole numbers. And hydrogen had a charge of +1, helium had a charge of +2, lithium had a charge of +3, and that's the number they gave it. Okay? They didn't know it was protons until they found protons later. But the reason why that worked is because the number of protons determines what kind of atom it is. So that's why they call it the atomic number, because it tells you what kind of atom it is. Okay, so on your periodic table, look at the key. It says it has an atomic number. You'll see it's kind of the organizing principle for the periodic table. You start with number 1, read across, and then down. They just keep getting bigger and bigger and bigger. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and then 19 starts another row. They're just in numerical order, based on the number of protons. Yeah, this is as current as I could get. 2017, 119, 120. They're in the process. There's some evidence they've made it, but yeah. Okay, so atoms are neutral. How can you have a bunch of protons and be neutral? You have electrons. How many electrons? Same amount. So the way an atom gets to be neutral, it has the same number of electrons as protons. As long as it's neutral. Now, the atomic number is always the number of protons. If it's neutral, it's the number of electrons, but it doesn't have to be neutral. They'll tell you what it is if it's not neutral. But it doesn't have to equal the number of electrons. It has to equal the number of protons. Because when I move the electrons away, I don't change what kind of atom it is. The protons stay behind. Okay. And here's the one that I think you've been mistaught before, is what usually happens. It's not your fault. The mass number. Second number they use to identify it is the mass number. And the mass number is the number of heavy pieces. Heavy pieces are protons and neutrons. So all the things with significant mass. If you were trying to figure out how heavy an atom was, we were weighing the parts, would the electrons make much of a difference? No, the fact is they wouldn't show up until the 4th sig fig. Right, they're 1/2000th, right? So if you left them off, you'd be off by 1/2000. That's 4th sig fig. That make sense? Okay, and so they call it the mass number because it's all the things with mass, with significant mass. So the atomic number tells you what kind of atom it is. The mass number tells you how many heavy pieces it has. Not how heavy it is, how many heavy pieces it has. Okay? Because the mass number is not on the periodic table. Nowhere on the periodic table does it show you the mass number. It has masses, but they are not mass numbers. Okay? The numbers on the periodic table are not mass numbers. So if you look and see, the one you want to use as a mass number, they say average atomic mass. Because yesterday we saw with the mass spectrometer that you have more than one kind of each atom. So if you say, how heavy is this kind of atom? You say, well, which one? Which one? There was two galliums. Which one? And the answer is, no, we're not going to talk about which one. We're going to talk about the average one. So that's what's on here is the average. Here's a clue that it's not a mass number. It has a decimal point. Can the number of protons plus the number of neutrons have a decimal point in it? All right, it's got to be a whole number. It's a number. So that key number tells you it's a whole number. Okay. We use the mass numbers to figure out what the average is. We'll talk about that math a little bit later. Okay. But the reason why the mass number is not on the periodic table is because of isotopes. And Dalton was wrong again. First, he was wrong about them being indivisible. Then Thomson and Rutherford found parts. Now he's wrong about the fact that every atom is the same. Every atom of the same element is identical. We saw yesterday, I was showing you two different kinds of gallium. Atoms of the same element can have different numbers of neutrons. They have different numbers of neutral pieces. And the next thing we do, you'll see that number of protons and number of neutrons affects whether an atom is radioactive or not. So they're the same element, so they're going to have the same atomic number. But they're going to have different mass numbers. Because if mass number is protons plus neutrons, same element's always going to have the same protons. You're adding different numbers of neutrons, so you're going to get a different mass number. So that's what an isotope is. An isotope is a specific kind of atom out of several. There's more than one kind of oxygen atom. There's 3 different isotopes of oxygen. We'll talk about what's holding the nucleus together, and that's part of the cause. Because you got to think about it. What you know is that likes repel. How come the protons stay together in that little tiny nucleus? The nucleus isn't neutral, okay? It can't be charged that's doing it. There's got to be something else going on. There's some nuclear forces that we're going to have to talk about. And actually, the nuclear forces are affected by the ratio of protons and neutrons. Okay, chemically they're identical. The only difference is mass. The only difference is how much mass they have. They react the same way. They look the same. They smell the same. Well, the atoms don't have a smell, but they look the same. React the same. Give off the same colors light. Yeah. So we're going to have to be able to describe atoms and include their mass numbers so we can talk about the different kinds of each kind of element. So we're going to use some symbols. Okay. The symbol for the element is on your periodic table. Most of them are based off the name of them, but the name may not be in English. Okay? So, surprise to some people that the symbol for potassium is K. Number 19. Okay, now the symbols you'll notice, 2 letters at most. First one capitalized, second one lowercase. That makes a difference. Okay? Why would that make a difference? Well, because those are different things. One of them is an element, cobalt, a bluish silvery metal. The other one has 2 elements because it's got 2 capital letters, and that's carbon monoxide, a poisonous gas. So if you're one of those block letter writers, make size significantly different. Okay? Uppercase first letter, if there's a second letter, it's got to be lowercase, so we know that the next uppercase is the next element. So that's the clue that you're adding an element, is it starts with an uppercase letter. Okay? And once you do that, I put X for where the symbol goes, and superscripts on the left-hand side. Superscript written above, super above, script written. Superscript on the left, mass number. Subscript on the left, atomic number. It's important that you use the left for that because we use the right side for other stuff. Because you've already seen that down here you write down how many there are. You don't want to put an atomic number there, unless it's hydrogen, maybe. I don't know. You wouldn't want to put uranium's atomic number there because that would mean that you had 92 uraniums, which is not what you have. Okay? And what goes up here is charge. We're not going to worry about the charge part right now. So when I ask you to calculate the atomic number, mass number, how many protons, neutrons, electrons, and to write the symbol includes the capital letter with the mass and the atomic number there. So we have to be able to talk about the different kinds of isotopes. So how do we write the names? Well, all you do is put the mass number after the name of the element. So carbon 12 has a mass number of 12. There's another kind of carbon called carbon 13. It has a mass number of 13. There's also a carbon 14. It has a mass number of 14. They're all carbon. They're all carbon. So they all have 6 protons. But they have different numbers of neutrons. Carbon 12 has 6 neutrons. Carbon 13 has 7 neutrons. Carbon 14 has 8 neutrons. And there's several kinds of uranium. The one that they make, they use in nuclear reactors and to make atomic bombs is uranium-235. And one of the hard parts was isolating that uranium-235 from the rest of the uranium. Okay? Because it makes up less than 1% of all the uranium, and you can't use chemicals to separate them. Okay? So one of the ways they separated them was, we talked about that mass spectrometer and how the light ones would turn more than the heavy ones. They actually just put the uranium sample in and separated it that way and collected the uranium-235 because it turned the most. So they did it one atom at a time as it went through. It took a long time to build up that uranium-235. When they dropped the bomb on Hiroshima, they did not have enough uranium-235 for another bomb. It was going to take them months to get it. Now, they had more plutonium for the second bomb, but the uranium, they'd used up all they could isolate. It was hard to get the uranium-235 from the uranium-238 because the only difference was it weighed less than 1% less. So it turned a little bit faster. So it was a big challenge to separate those two. Okay, so let's practice a few of these before I set you off on your own. For this, 2411, Na. So you need to look all over the table for Na. No, you don't. Just find number 11. Okay? Everybody can see how I could just use number 11 to find it? Okay. What is the number of protons? How many protons does this have? Well, what number tells me the number of protons? Atomic number. So this has 11 protons. How many neutrons? Yeah, so this number, the top number is protons and neutrons. This number is just protons. So if I subtract, I get just neutrons. Right? So 24 is protons and neutrons. 11 of those are protons, so I have 13 neutrons. So they set up this subtraction problem for you. That's kind of nice of them. How many electrons? Okay. Since this doesn't have, I said we'd put a charge up here and there's nothing there. So it's neutral, so it's got to have the same protons as electrons. So that would be 11. What is its atomic number? 11. It's the number of protons. It's what? Hey, what's its mass number? It's written right there. It's 24. Not a lot of math in that when they wrote it down. Okay, what's its name?
Sodium.
Hey, everybody write sodium, and I'm going to mark them all wrong.
Na.
What's the last thing you wrote before I gave you an example? That's the last thing you wrote before I gave you this example, wasn't it? Okay, we're just doing exactly what we said we were going to do. We write the name, you put the mass number at the end of it. Are you okay with that? Because there's more than one kind of sodium atom out there. Yeah. As long as it's neutral. And when it's not neutral, we stop calling it an atom and start calling it an ion. Okay, but so for today, everything's going to be neutral. Eventually, we'll switch that up. Okay? Because electrons can move around. Really? So, let's try it the other way. An element has 91 protons, 140 neutrons. Hey, what is its atomic number? Well, atomic number is the number of protons, so it's got to be 91. What is its mass number? You got to carry a 1. $90 plus 141 is 231. Okay, so we need to go back and practice adding, addition. Okay, I don't have time to teach you addition, okay? Number of electrons. Well, it was neutral, so it's going to be 91. Complete symbol. Yeah, PA is not the complete symbol. Okay, first of all, how did they know it was PA? Because the atomic number was 91. Okay? And so that 91 is the atomic number, so it goes down at the bottom. And the mass number goes up top, the 231. There's no charge because it's got the same number of protons as electrons. Okay, what's its name? Protactinium. 91. Protactinium 91. What was that? No, it's not 91, is it? 231. Good job. All right. Learn from mistakes. Don't just copy stuff off the screen, folks. You're supposed to be engaged. Okay. Hey. No, my bro's not mean. Number of protons.
35.
It gets pretty easy pretty fast, doesn't it? Number of neutrons.
45.
They set the subtraction problem up for you. They set the subtraction problem up for you. Okay, pretty easy. Hey, number of electrons. 35. Atomic number.
35.
Mass number.
80.
80. Because it's written on there, right?
Bromine 35.
Yeah, all bromines are 35. This one is 80. Right? All bromines are 35, but protons, this one has a mass number of 80. So 35 is what bromine has in common. You don't want to write down what it has in common because you already wrote its name. And we don't want to be redundant again. Okay. An atomic number of 34 and a mass number of 78. What is the number of protons? Protons is the number of is the same as the atomic number, so that is 34. Number of neutrons. Okay, we're going to have to work out some subtraction issues. Okay, we did addition. Okay, number of electrons. 34. We're getting better at this. Complete the symbol.
SE, and then on the top there's F78.
Okay, so they knew it was SE because the atomic number was 34. And if the atomic number is 34, it gets in there. And the mass number gets written up top, 78. So this is selenium, named after the moon. Selenium.
78.
78. Okay, so pretty straightforward. Okay, and this is what you guys have done before, right? This is old stuff coming back. Right? That's what people have you do about atoms the first time they teach you atoms. They tell you about protons, neutrons, and electrons, and then they have you count them, right? Well, we figured out how they knew protons, neutrons, and electrons, and now we're going to count them because it's important how many there are. Yeah.
So, say, for experiment, if you experimented and you found that Thomson was wrong, what does a scientist do at that point?
They publish a paper. They publish a paper, and they call up and talk. And Thomson was agreement, but they just say, "Give me up." So they go and they argue in journals. You have to publish your evidence, and then some. Then when you publish your evidence, the people who disagree with you write you letters to the journal, and they have arguments in letters to the editor about how lousy your data is. But that's how you get to the truth. Yeah, sometimes the interesting stuff happens in the letters to the editor. Okay, I will always provide you a periodic table on the test. It'll look like that. It won't be that one because you may have accidentally written some stuff on yours that you shouldn't have in front of you during a test. So I will always provide one for you. You don't have to memorize it. Okay, the top and the bottom are the same. But I'm going to suggest, okay, there are shortcuts to do this really fast. And if you take those shortcuts to do it really fast, you're going to skip the decisions across the row. Okay, work your way on the same row all the time. Try to fit a row at a time. That's the right way to learn it. You can do it faster than that without thinking, and that would mean that when I ask you to think on the test, you haven't practiced that thinking.